Hello. Here we go. So Anil decided to take the easy step and just sit in the audience and listen to his talk. You're going to have to deal with me up here. And we're slowly getting started up here. I would love to take a break. Can somebody bring me the coffee up here?
That's the one.
So Brian ended a little early, so we have plenty of time. You're going to get to your coffee break in time. Don't worry, guys. And those were very interesting talks, and I'm actually going to refer back to them. The two we just saw the last slides of. Absolutely. Hey, there we go. Thanks so much. So let's see whether I can operate this. So you have heard the talk by Technica about rings. We've heard the talk by JLR about 10BASE-T1S. We just heard Brian talk about the problems of CAN and packaging CAN and all of these issues with bandwidth and interrupts and so on. I want to take the next step after that. So look at this not as a solution as we want to do it today. The last few talks have done that, I think, plenty, talking about what we need to do today. Take this as sort of the lighthouse. This is where I think we want to go and solve some of these problems in a more futuristic fashion than, quote unquote, in a today's fashion. So the first thing, of course, is the service orientation. I could not help but put a screenshot of Lars's slide here. Lars being one of the fathers here of some IP, and that was the first time that service orientation actually entered the automotive world. And Lars made a very good point in Munich beginning of the year. It is freaking difficult to design good services. And Lars had this slide on here where he says everybody wanted to do everything service-oriented, and they basically failed, and now they're falling back. What I'm saying is, well, don't go all the way back. Let's actually keep the dynamics up and make sure that we understand what services are. How does a service of the future look like? And then maybe we can actually continue on that curve without the boom, without the explosion. So what do we need to do in order what we call a service and how we handle services in order to make this work and actually continue on that curve and introduce what I would call services into the SDV, into the software-defined vehicle? Because if we want to have this software-based, if you look how software is deployed with Docker and with other orchestration technologies, it is always service-based. So how can we take that, and what do we need to do in the future in order to bring that into our vehicles? To me, a service, be it a micro or another service, needs to definitely offer what some IP offers since 2000 and what is it, 13, whatever, 11, subscriptions and RPC methods. So calling a function, asking a server to do something for you. I think it is very important to have the service discovery underneath. To me, service discovery is one of the differentiating features of a service versus a different kind of communication. Knowing what is going on in the system is important, and offering services only when they are available and functional actually makes your whole communication system a lot less prone to errors. Now, the problem is if you design your services too large, that's why there is microservices in the title, then actually fulfilling this requirement that the full service is available when you announce it becomes rather difficult, and you end up with these elements in your data, oh, not available, not filled, whatever, and things become very complicated. If we make them microservices, that also means we have micro software. So we can very granularly update our software if we want to change a single small feature. And that's part of our problem, right? That we always need to update this huge software block. So let's break it down and make that smaller. And what is, again, a very important point to me is the versioning and the instantiation. If we have versions to our service and we have clear rules what a service needs to do in order to go from a minor version to the next minor version, or from a major version to the next major version, then we see compatibility issues very quickly. We see on the communication, these two ECUs will not communicate with each other because they use version 1 and version 10. Those will definitely not talk to each other, and it will make our debugging a lot easier. So what makes a service a service? To me, there is two elements that define a service. The first one I already mentioned, it's the service discovery. And the second part is what I call the service contract. So let's get into the service discovery. What does it do for us? And a lot of people think the service discovery tells me sort of, I learned something new about the system. There is nothing new to be learned about the system in the vehicle. We know exactly what it does. What we need is the runtime information. We don't need to learn that this vehicle has a camera. We know it has a camera because we built it in. What we need to know is what state is that camera in? Is that camera available? So I'm not trying to talk to a device that is not ready to be talked to. Yeah, that's kind of pointless. If you try to talk to me before I had my first coffee in the morning, you might as well not do that. I put on my smiley face as service discovery, and then you can know you can come and approach me. Yeah, we give the last details of how to reach the service, and I say last details because we know sort of roughly how this will work. We put the topology together, but we might have changed an IP address. But it's still the same service, right? Just because we change an IP address, we don't want to change the configuration of the host software. We can actually, with some of the mechanics that Brian has sort of subtly introduced, we can do dynamic network configuration. Like you can do snooping on the service discovery and configure your multicast or groupcast forwarding. We can make we can make other protocols, like for example ARP. If you have service discovery, you are communicating your IP address and your MAC address. There is technically no reason to actually have ARP running in between. The only reason it's still running is because people were a little too lazy to actually update Linux drivers to do that properly. And of course, a lot of people say, you're breaking my ISO-OC layer model. Well, I'm happy to break your model if I can make your life easier. So, service discovery, to me, a very fundamental point of a service, and I think we need service discovery for every communication that we're doing in order to avoid expecting and using functionality that is not there. The next is the service contract. The service contract has multiple elements here, and I'm not going to read through all of those. What I do want to point out, a lot of people today think that it's only a service if it's, for example, some IP. And I completely disagree. Yeah? In the service contract, we define what the protocols are that we use. What is the serialization? What is the header around that? But that service might be a camera. I'm offering you a camera image as a service. You subscribe to my camera service. You subscribe to the image, and whether I deliver that image to you in 1722 or whether I deliver it to you in RTP or whatever, that is defined in the service contract. There is also no point in trying to agree on these details dynamically, like one server requesting it in one format, the other server in the other. We build the camera. We know what kind of formats it supports. There is no point in overcomplicating this whole thing. What I also want to point out, because some people have at AEC talked about the topic of QoS in our vehicles. The service contract needs to also provide the QoS. We need to know the QoS from the beginning. There is no point in trying to argue in the vehicle, oh, I need this within, I don't know, 5 microseconds, and then you realize it doesn't work. All these dynamic QoS protocols in the vehicle, in my opinion, will not work because you cannot live with an answer of no. We need to make sure that the answer is there, and we need to write that down into our service contract. And the same is true for the security. We need to know what kind of security is on top of this, because when we did service discovery at the very beginning, back sort of 2009 timeframe, I guess, we wanted to do this all dynamic, do everything dynamic. But if you try do that, you basically leave the door open for everybody to use everything. And then you don't have any security at all. So the security measures need to be part of the service contract. We need to know upfront who takes care of security and what are the mechanisms that we use. And we talked about it, I believe, yesterday. Do we live with authentication? Am I happy to know who you are? Or do I also need to check, okay, I know who you are, but I also want to check, can you execute function X? Can you execute function Y? Can you use service whatever? And we need to extend our databases that keep this information, what some people call their K-matrix. We need to extend those information databases with that information. And I'll let you read the rest of those and not go into all the details there. Instead, I want to take the next big point here, zonal architecture. And I am idealizing zonal architecture here. We can have a long discussion, and I had a nice discussion just before the last talk over in the exhibition hall, why people are currently, in my opinion, not doing zonal architecture. So in my view, zonal architecture is really when we connect sensors, actuators, based on geometric location. And one big OEM the other day published their quote-unquote zonal architecture on LinkedIn. If you want to look back, to me, that is not zonal architecture. So we want to do this mixed through the different domains. And don't take this as a complete list, but you can see cameras, brakes, radars, they all need to be able to connect to the same aggregator. And they need to connect to those rather simply, very easily. And one of the premises of this is that communication goes on between the zonal controllers and the HPCs. There is very little, or hopefully in an ideal situation, there would be no communication between the zonal controllers. It would all be going into the HPCs, out of the HPCs. And in this case here, that basically turns this whole thing into sort of the star architecture. Yeah, you have the HPC cluster somewhere in the middle, and you branch out into this radiating star. Now, a lot of people say we could turn this into a ring, and we saw from technical engineering that rings have their, let's say, their fanciness. And obviously that is doable. You can easily imagine turning this star into a ring. You get some disadvantages, some advantages. We can have that discussion at a later time. What makes it actually zonal on the device level? So again, HPCs handle the compute tasks. The zonal controllers connect the sensors and actuators for all functional domains. And we have a very, very small network. We basically go out of the HPC, we go into the zonal controller, and then maybe we have one more hop out onto another link. So it is a very small network, which actually makes this whole discussion about the TSN, latency, and so on. In this kind of a small network, a lot of the discussions that were based, or where TSN is based on, they basically go away. We connect to the zonal controllers. We don't connect to any other devices. I'm gonna put a little bit of a relativity to that. And we want the devices that are connected to the zonal controllers to be as dumb as possible. And when I say as dumb as possible, I actually mean a little bit different things than a lot of other people. I would imagine that we actually connect more like analog sensors to our zonal controllers. As soon as we make them into network devices, as soon as we put a CAN, a 10BASE-T1S, or 100 megabit onto those devices, I think they should already be smarter again. Yeah, I think that would be part of the software-defined vehicle. Do we want to be able to have these smart sensors and connect them to the zonal controllers? But then I would argue we actually want to update them. If they can't do that, well, then pull that intelligence into the zonal controller. Now, obviously, a lot of people are going to say, yeah, but I have components that kind of need to stay together. Well, if you have an engine controller, call that your zonal controller for the engine. If you have a skateboard, you have that skateboard module as one of your zonal controllers. Yeah, let's not make this religious. Obviously, a zonal controller or a zone can be a very, very smart thing. I would call a door module easily a zonal controller. So I think we started out this discussion on zonal controllers. There's 4 in every corner, 1 left, right, front and rear. I think in this architecture there need to be a lot more zonal controllers than 4, because otherwise these things grow into huge animals. I remember a time when I was working with Hari and we were trying to do zonal controllers, and they ended up with connectors all over them, yeah? And as soon as you end up with 800 pins on a single box that you need to connect to, that's just not gonna work. So let's make these zones a little smaller, keep them actually geometrically, but not overdo this. Why zonal architecture? And this goes back to what I asked the gentleman from JLR beforehand. Unfortunately, I forgot his name, I apologize. Again, a slide from beginning of the year that Martin Hiller of Volvo presented. Your vehicle uses roughly 20 gigabit of data overall, everything that it communicates. And this is actually a rather high-end vehicle, as the slide is from Volvo. But if you look at it, 18 gigabit or probably more of that is your cameras. You can easily run a vehicle. If it doesn't have imaging technology, you can easily run it on 2 gigabit or even less as the overall communication load in the full vehicle. And that's why we're struggling as an industry to introduce higher line rates, right? And that's why we need to solve these problems that Brian talked about. We don't have a motivation to actually put high line rates into the system because our video links go back to some device. And so the video links basically move out of this architecture. They're a complete separate domain in themselves. So if we think about maybe some of those radars or lidars actually go into the imaging sense, they might move over to the camera, but these cameras are what actually drive our bandwidth. And now the question is, why did Ethernet push away something like SDH SONET? It is all about what we used to call triple play in the 2000s. I today have fiber to my home. Do I need a gigabit fiber to do a telephone call? I obviously don't. Do I need gigabit fiber to do my internet? I probably don't. Do I need fiber to stream my TV and to do my entertainment? I probably don't. But combining them all together, that justifies putting the gigabit line into my home. So if we can justify, because of our video and our imaging technologies, to actually put high data rate to our zonal controllers, then we're resolving all of those problems that Brian has talked about, that the gentlemen from AD and JLR have talked about before, because now we have a justification to put what I call a network controller here into the zonal controller. And in the past, we always wanted to make the network invisible. When I started in Ethernet, everybody said the network infrastructure cannot cost any money. Yeah, the network infrastructure must be invisible. It must be cheap. It must just be there. there is no management, and then we walked our way up to having PTP implementations. If we have this kind of line rate, because we have our cameras connected to our zonal controllers, we suddenly get all of these benefits that the network controller can take away a lot of the network load from the ECU. We can offload something like network management. Even the power control could go onto the zonal controller, and we don't have these parallel networks and this fiddling around with the NM doesn't put the vehicle to sleep, and the single ECU can drain our battery. Service discovery, even software over the air update. If you only have, let's say, 10 of these zonal controllers and you equip them with dual bank NVM, you can do the update through the network device while the vehicle is running, and nobody else will even know be the wiser. And then eventually, when you're done with your update, you boot the vehicle in the new configuration. If you need to put dual RAM into dual NVM into all your ECUs, that's not going to work. That's so much of an overhead, you can't do that. But if you can concentrate that overhead into your zonal controllers, then you actually get those advantages, and you get the advantages from the hardware support of that network controller, of that network attachment device. The network attachment device can also take over your protection. Obviously, we don't want a sensor or a camera to completely overload the network. So we can put that kind of scheduling or shaping or even policing into the network controller. And the other way around, if we do have a CAN device or whatever, or a 10 megabit device, we don't want the HPC to overload that device either. Either all of that can go into the network controller. And the same is true on the HPC side. And I do want to point out what Marcus was saying yesterday, the whole story about DMA, and Brian was referring to it as well. If we can transfer the data through DMA, through an interface like PCIe, into the memory of the application, we can go from all of this interrupt load that was just talked about, we can go to a polling mode. We have a schedule that runs in our operating system, and the data is just in place. It has been pushed there through DMA, through hardware, and the application can access the data it expects, and there is actually no interrupt load from all of those messages. And again, we can offload a lot of functionality, and I'm taking a lot more time here than I intended, so let me come to the conclusion. Including the cameras into the zonal architecture, including the imaging devices, be it cameras, LiDARs, radars, attaching those to your zonal controllers, and that's what I asked the gentleman from the JLR-AD discussion beforehand. That is your excuse to get 10 gigabit or maybe even more to your zonal controller. And once you have that, this whole problem about, oh, I can't put a single CAN frame into a single Ethernet frame, all of that goes away. We gave this presentation a while ago at one of the IP Tech Days, I believe 2021. I had the reference up beforehand about what we call the free rider principle. Once you have a 10 gigabit link to that device, and again, you don't do that for the latency. You do it because you have imaging technology connected. But you get all the benefits of the latency on the side without even asking for them. So this is the excuse that I was kind of hinting at in my question beforehand. And with that, I'm going to close it here for questions, and thank you for your attention.
All right, thanks, Max. And we will open up to questions.
Why?
Thank you very much. You say a lot that we want to say, so thanks for that. Also refer to Volvo. And we do have a vehicle with service-oriented architecture.
I know.
So try out EX90. Okay, so my question is that when the lesson learned or the pain point when design service-oriented architecture is that people associate service with event, Well, so connect to the communication. So always people think that, okay, then I have to do the event communication. And then for automotive, many times we want to use the periodic. So that's one misconception. Another misconception is that the people think that, okay, we had to use, because of service-oriented, we had to use some IP. And then when some IP can also use for signal, right? Signal-based.
Exactly, it becomes the same thing. Again, we need to make sure that we extend this idea of we consider a service, we need to extend that. As long as we just talk about some IP as service, that's not what we're talking about here, right?
Yep. And then my question is, you're talking about microservice, but when we decide the vehicle architecture, we think that we have a vehicle control, where is in the HPC. And then we have a low-level control, which is located in the zone closer to sensor actuators, right? So the service usually used in the HPC. And then to be able to provide a service, let's say vehicle speed, you need a lot of sensor and data to be able to calculate that. So how do you solve this dependency if you have a microservice?
I would argue that you can offer your services also from your zonal controller. And the question is, what does the zonal controller now offer? And this is where you have, I think, a lot of variety of what you call a service. Does your zonal controller offer you an I2C interface and it says, I have an I2C interface and I offer that to you as a service, you can access it over me? Or does the zonal controller say, I have an audio system and you can actually, through my RPC service, you can control the volume? Those are very different levels of services, but they all, this doesn't allow me to go back, I guess. Does it allow me here? No, I can't go back, doesn't matter. Any of these services need to fulfill the requirements that are listed on the service discovery and on the service contract. What you do in that service is very, very flexible as long as you have all of those elements available.
But again, thank you very much for very interesting talk.
Thank you.
It's a great presentation, Max. I'm wondering, one of the statements you made was about microservices. You cannot dimension your services to be too large. So I do not consider myself an expert in microservices. What I found is when I occasionally read about microservices or microservice architecture, oftentimes what you read, the articles are somewhat philosophical. And they leave it to your imagination as to what is actually a microservice versus a macroservice without any tangible examples. Do you have any example that you can think of how, of an example of where you would cut the service to be too large and how you could, in such a case for an automotive example, maybe structure it into a smaller set of microservices? What is the practical guidance for dimensioning your services correctly?
We're back to Lars' slide. It is effing difficult to design a good service, no matter whether it's macro or micro. This is a serious challenge. My criterion that I would apply is how certain am I that all elements that I'm providing in that service are definitely available at the same time. Do I ever see a chance that whatever I have clustered into that service, two pieces, one of them might not be available due to whatever reason? If I see that chance, put them into two services. If I am certain that these are available, like let's say with a camera, if my camera is available to send me data, then I guess the interface to control the exposure and control the camera is available, yeah? But if I say I offer a service that has two sensors, because I have two sensors connected to my zonal aggregator, well, if the one sensor fails and I don't have that information to put into the service, now I'm technically not supposed to offer that service anymore. So I think it takes a very diligent hand to find that separation, and I would argue you probably need to run through an iteration and figure out this was too big, let's cut it down smaller.
Okay, Thank you very much.
Thank you, Marcus.
Any additional questions? All right. I think we're good.
Hey, thanks
Thank you, Max.
everybody.